Morning. We are looking at finding the area of a segment today. So what we have is a chord. A chord is a line that goes from the circumference on one side of the circle to the other, but not through the center, and it splits a segment into two as shown, okay? So we have our minor segment is our smaller segment, and our major segment is our larger segment. So we consider a segment cut off by a chord in a sector of a circle with a radius r and a central angle theta. The segment is minor if the central angle is less than 180 degrees or pi radians. It can be acute or obtuse, okay? And we can find the area of the minor segment by subtracting the area of the triangle from the area of a sector. So our area of a segment, how we find that formula is that area of a sector minus our area of a triangle. Okay, so in our diagram off to the right, what we have is we have our little minor segment in there, but we have our sector attached. So for our area of a triangle, what we're going to use is, this is trigonometry, so we're using our area of a triangle formula for trigonometry, which means we're going to be using our A equals a half AB sine C, okay? And so that means that our area of a triangle is going to equal a half times, well, our A and our B are our radiuses. So it's going to be a half times our radius times sine C, so sine theta. Okay, so we have our angle in the middle is our C, and then we have our two sides are our radiuses. That means we get that our area of a triangle formula that we're going to be using is a half r squared sine theta. Now, for our area of a sector formula, that's what we used and learnt about last lesson, and so we are going to use our formula A equals a half r squared theta. So in order to find our area of our segment, we need to use these two formulas, and these two formulas are on our reference sheet, our area of a triangle and our area of a sector, okay, to find the formula for area of a segment. So our area of a segment is our area of our sector, which is a half r squared theta, minus our area of a triangle, which is a half r squared sine theta. Now, what we get with our area of our segment formula is we can see that in both terms in our formula are a half r squared theta and our second term, a half r squared sine theta, they both have the common factor of a half r squared. So we can factorize out that a half r squared so that we have a half r squared lots of theta minus sine theta as shown. Okay, now our area of our segment formula is not on our reference sheet. It's one that you need to remember. That's why it's important that we know how to get to the formula as well in case we were to forget. Now, we can also see that what happens when a segment is major. So if a segment is major, it's when the central angle is more than 180 degrees or pi radians. So it's a reflex angle like you would have learnt back in year 7 or even in primary school. So we can also find the area of a major segment by finding the area of the triangle and adding it to the area of that sector there, okay, in order to find that whole amount. So what we do is we write that our area of a segment is equal to our area of our sector plus our area of our triangle. So with our area of our triangle, again, we're going to use that a half AB sine C formula. Okay, but it's not as easy to see what our angle is in our area of our triangle. So for our area of our triangle, I'm just going to draw my triangle off to the side here. What we have is we have our two radiuses, okay, but our angle theta is our angle in the segment, not inside our triangle. So that means that our angle inside our triangle is going to be 2 pi minus that little theta in there. So what that means is when we find our area of our triangle using our formula, it will be a half times r times sine in bracket 2 pi minus theta. So what we will have is a half r squared sine 2 pi minus theta. Okay, but we don't want sine 2 pi minus theta. We need to use our ASTC symbol, our angles of any magnitude. Okay, and where is 2 pi minus theta? It's going to be in our C quadrant over here. Our 2 pi minus theta is over here in our C quadrant. Okay, so is sine positive or negative there? It is negative, so that means that sine 2 pi minus theta is equal to negative sine of theta. Okay, because it's going to be negative there. Now, if you're thinking, what happens if it is an angle that is more in our triangle that's between 0 and pi, okay, and it's more than pi on 2 or more than 90 degrees, it's still going to be negative because it would be in our T quadrant there as well. Okay, so what this means is that our area of a triangle, when we have our major segment, is equal to minus a half r squared sine theta. Okay, so we've taken the minus sine theta and we've substituted it in, but put our minus right out the very front, like so. Now for our area of our sector, that is nice and easy. We can just use that formula from our reference sheet, A equals a half r squared theta. So what this means is for our area of our segment, we have that it's our area of our sector, which is a half r squared theta, plus our area of our triangle, which is minus a half r squared sine theta. That means that we'll have a half r squared theta minus a half r squared sine theta. Again, we have that common factor of a half r squared theta. So we can factorise that out. So we'll have a half r squared, lots of theta, minus sine theta. So that means that our area of our segment formula is the same for both our minor and our major segment. Okay, so if you need to write a note on that, you can. So note, formula is the same for minor and major segments. Okay, just how we get to those, that formula for area of our segment is just a little bit different depending what size segment we have. Probably the same for minor and major segment. Okay, turn the page when you are ready, and we're going to have a go at some questions. So, like I said, we have our area of a segment formula is our A equals a half R squared theta minus sine theta. Now, that is not on our reference sheet. So this is a formula that you need to remember. It's maybe something that if you have a study aid, you make sure it is definitely on it, whereas some of those other formulas, you don't need to use the space on your study aid for. But it's also a formula that when you're going into an exam situation where you don't have anything that you're taking in with you, such as the yearly exam, I would be writing that down as soon as I'm allowed to pick up my pen. Okay, our A is our area of the segment, our R is our radius of the circle, and our theta is the central angle subtended by the arc. And this is all measured in radians. So our first example here, we want to find the exact area of the minor segment formed if it subtends an angle of pi on 4 at the centre of a circle of radius 5 metres. Now, the first thing that jumps out to me is we want to find the exact area. So that means we're going to be leaving this in terms of pi or surds. Okay, so that means that we can't, if we don't have the new calculator, we can't just put it into our calculator because it's going to give us decimals. All right, so we need to be able to do the work for us. Now, that formula is our A equals a half R squared theta minus sine theta. And in the question, we are told that our radius is 5. We're also told that our angle is pi over 4. So we can substitute in our radius and our angles to have A equals a half times 5 squared, lots of pi on 4 minus sine pi on 4. Now, the first thing that we're going to do here is tidy up what's in front of our brackets, which is our half times 5 squared. So with our half times 5 squared, it works out to be 25 over 2. Okay, because 5 squared is 25, times that by a half, you get your 25 over 2. So when we're leaving in exact forms, we want no decimals whatsoever. Now, there is nothing that we can do to tidy up our pi on 4. However, we can tidy up our sine pi on 4 because that is an exact trig ratio. So our sine pi on 4, we can use on our reference sheet. We have our triangle for pi on 4. Okay, we have our pi on 4 is our isosceles triangle with a hypotenuse of root 2, but that is on our reference sheet, so we don't have to draw it. But what we have is that our sine pi on 4 is going to equal 1 on root 2 because we have our opposite and our hypotenuse. So, whoops, I shouldn't have closed that bracket. What we have is we have 25 on 2, pi on 4 minus, instead of sine pi on 4, we're going to have 1 on root 2. Now, this isn't in its nicest form possible. So what we're going to do is we're going to expand our brackets to start off with. So when we expand our bracket, we get 25 on 2 times pi on 4, which is 25 pi over 8, minus 25 on 2 times 1 on root 2 is 25 over 2 root 2. Now what we need to do is we are going to rationalise our denominator. So when we're doing this, we want to make it all one fraction. And the first step is to make sure that both aspects of our fraction have a rational denominator. Now the second part doesn't, so we need to multiply the numerator and the denominator by the irrational part, which is our root 2. Okay, what we do when we do that is we get our area equals 25 pi over 8 minus 25 root 2 over 4. Now, we want to make the denominator of the fraction the same, so we want to make this one fraction. How can I make this one fraction? What do I need to have the same to make this one fraction? Yeah, so we need to make this one fraction by having the same denominator. So we need to times that second fraction by 2 so that they'll both have the denominator of 8. So that means our area will equal 25 pi minus 50 root 2 all over 8. And then we just need our units. So our radius was in terms of meters, so our area is in terms of meters squared. Now, if you have the new calculator, I believe that you can just do 25 on 2 lots of pi on 4 minus sine pi on 4. And no, because you're in radians. Hang on. Let's see if I change it to radians instead of degrees. I'm not sure if it's going to give it to you in the exact form because of the pi. Okay, it's going to want to change it. But if it does work, then it's going to save you some time. Otherwise, when we ask for exact, we need to make sure we keep it in exact and we get it to its simplest form. So its simplest form is with a rationalised denominator and all over the 1 denominator. Okay? Our next example is to find for an angle of 2 pi on 3 at the centre of a circle with radius 9 centimetres. We want to find the length of the chord. So in order to find the length of a chord, it's going to help us to draw a circle. It's going to help us to put our radiuses in. It's going to help us to draw our chord. And so what we have is our radius is 9. And we have our angle is 2 pi on 3. And we're trying to find the length of our chord. So the length of our chord is this distance here, which we're going to call x. So in order to find the length of our chord, if I was just to take the circle away, all we are left with is a non-right angle triangle. So in my non-right angle triangle, how can I find my length x? Well, I have 3 sides and 1 angle. What rule do we use when we have 3 sides and 1 angle? Yeah, we're going to use our cosine rule. So we're going to use our cosine rule, which is c squared equals our a squared plus b squared minus 2ab cos c. All right, so we will have our c is our x. So x squared equals 9 squared plus 9 squared minus 2 lots of 9 cos 2 pi on 3. Now, because we have cos 2 pi on 3, we need to make sure that our calc is in our radian mode. Okay, because we're dealing with radians, not degrees. When we put this into our calculator, we're going to get x squared equals 243. So x will equal the square root of 243. And x will equal 15.5884 ... which we want this correct to 1 decimal place. So we'll get 15.6 centimetres. Okay, we don't want to forget our units in there. Now for part B, we want to use that exact same information to find the length of our arc. So our arc length formula is on our reference sheet. There's no reason not to know it. It is our L equals R theta. Okay, in this question, we've been clearly told that R is 9. We've also been told that theta is 2 pi on 3. So that means we'll have our arc length is 9, stay still please, 9 times 2 pi over 3. And what we get is our arc length is equal to 6 pi centimetres. Okay, so with our arc length, we want to leave it in exact. So we just want to work out what 9 times 2 on 3 is and leave it in terms of pi. Our last bit is to find the area of the minor segment correct to 2 decimal places. So what we will have is our A equals our 1/2 r squared theta minus sine theta. So we have that again, our r is 9, our theta is 2 pi over 3. So we're going to have A equals a half times 9 squared lots of 2 pi on 3 minus sine 2 pi on 3. Now this question is nice to us. This question asks it for correct to 2 decimal places. So because it's correct to 2 decimal places and it's not exact, we can just put it straight into our calculator to get our area is 49.74989 ... So our area will equal 49.75 centimetres squared. Alrighty, flip the page when you're ready. We have one last example. It's not going to take us the whole page. I've just allowed for the whole page worth of working out. So don't stress. Okay, so for our example 3, we have an 80 centimetre piece of wire is bent into a circle. A 10 centimetre piece of wire is joined to form its chord. We want to find the area of the minor segment cut off by the chord, correct to 2 decimal places. Okay, we are going to put this information on a diagram to make it easy. So the first thing we're going to do is we're going to draw our circle. Okay, we're going to put our centre of our circle. We're going to need radiuses. We have our chord like so. Now we're told that a 80 centimetre piece of wire is bent into a circle. So what that means is that the circumference of our circle is 80 centimetres. Okay, so we have circumference equals 80 centimetres. That's our first piece of information that we're given. The next bit of information that we're given is that our chord is 10 centimetres. So that distance there is 10 centimetres. Now we are being asked to find the area of this minor segment here. So the bit I have coloured in pink, that is what we're being asked to find. And we know that there is an angle in there and that these 2 side lengths are worth our radius. Now we have enough information here to find the area of the minor segment. We just first need to find our radius, we need to find our angle theta, and then we'll be all good to go. So in order to find our radius, we're going to find the radius using our circumference. Okay, remember our circumference of a circle formula is hidden on our reference sheet. Okay, but we have our circumference of our circle is C equals 2 pi r. Now, we don't know what r is, but we know that our circumference is 80 will equal 2 pi r. We can divide both sides by 2 pi. And that gets us that our radius is 80 divided by 2 pi is 40 over pi, because 80 divided by 2 is 40, and then we have that pi left. The next thing we want to do is we want to find our theta. So in order to find theta, what we need to do is we just need to look at the triangle that we have been given. Okay, we now know, so we have that our chord was 10 centimetres, but we now know that our radius is 40 on pi for both our radiuses. And so our angle in there is our theta. What rule can we use to find theta? Cosine rule. So we're going to find theta using our cosine rule for an angle, which is our cos C equals A squared plus B squared minus C squared all over our 2AB. Okay, so our C is our angle that we're finding, and the side C is opposite the angle that we're finding. So that means we're going to have cos theta equals 40 on pi squared plus 40 on pi squared minus 10 squared all over 2 lots of 40 on pi, lots of 40 on pi. Now, when we put just our fraction into our calculator, we get that cos theta is equal to 0.6915748625. So that means theta will equal inverse cos, or cos to the power of -1, of that 0.6915 ... Okay, and our calculator should be in radians. So it's 0.807292138 radians is our unit of measure that we want to be using. Now, that is our angle theta. I'm going to store that in my calculator as A. Okay, I'm just going to write a little A in brackets next to it so I don't forget in the next 2 minutes which letter I've stored it as. Okay, and now we have enough information to find our area of our minor segment. So our area of a minor segment formula is A equals a half R squared lots of theta minus sine theta. And we have that our radius that we're using is our 40 on pi, and our angle is our 0.807 ... So what we will have is A equals a half lots of 40 on pi squared, lots of 0.807 ... minus sine 0.807 ... Okay, lucky for us, we get to do this correct to 2 decimal places. So we get to put this straight into our calculator. A equals 6.87560 ... So area is equal to 6.88 centimetres squared.